What's up guys, I'm back with another educational video, and today's topic is all about logic gates. Now, in this video I'm going to assume that the person watching this has no experience with logic gates whatsoever, so those more advanced may find my explanation slow and monotonous. The second part of this video will be a bit more in depth on how we can apply logic gates to more complex situations. Anyhow, I'm going to go ahead and dive right into the meat of this video. First, let's focus on what a logic gate actually is. A logic gate is essentially either a real or hypothetical transformation to data in a circuit. That may be a bit hard to actually think about currently, so let's try to put it in terms of everyday life. Everything has terms and conditions, whether you download an app or if it's your grocery list. For example, if you're deciding whether or not you need bread, you may look into your pantry and see if you currently have any. If you do not, you'll buy some. You are operating under the condition that you will only buy them if there is none left. This might be very loosely translated into code as, if bread equals 0, then buy bread. Note that I said loosely. Code very obviously is not that straightforward, otherwise I would have memorized it by now. But it helps show that logic is in all decisions. Here's another example. Imagine you want to wear a red shirt with stripes. It has to have both. It cannot just be red, and it cannot just have stripes. This might loosely look like this. If shirt equals red and stripes, then wear the shirt. If shirt equals red or stripes, or neither, then keep looking for a different shirt. Notice that we only wear the shirt if, and only if, it is both red and striped. If it is not red, does not have stripes, or has neither, then we keep looking for certain shirts. Logic gates are extremely similar to this. They help us compare certain values in order to explain relationships among daily things, such as shirts. The key thing to remember is that logic gates typically refer to mechanics or circuits, but their idea is also carried over to coding. I'll make sure to focus on both in this video, but I'll lean more to the coding side. Let's start off with the extremely easy to understand logic gates. Almost all of them can be related to a word within the English language. For example, the AND gate. The AND gate basically says that if you have two values, both must be true. In real life, if you said the Statue of Liberty is in New York and is red, you'd be wrong. Even though it is in New York, it is not red. This gate is similar. Even if the first value is true, the second value must also be true. Let's see what it looks like in terms of numbers. Hold on, I know the picture may look super confusing at first, but just bear with me for a bit. Basically, if any value is a 0, it is considered false. If any value is a 1, it is considered true. This is known as binary or Boolean representation. You have likely seen this a lot in terms of people talking about coding. So as we see now, if A is false, the output is false. If B is false, the output is false. If both are false, the output is false. If none are false, the output is true. Pretty simple, right? It works just like our previous example of the shirt. Only if it is red and has stripes will it be true that we can wear it. This gate is represented by this symbol in coding, and you may see a code written like this. If shirt equals red, and shirt equals stripe, then wear. Notice how we said shirt equals twice. This is essential in coding, but it's not what I'm going to go about over here in this video. Our next gate is the OR gate. If you were to tell someone that you would like this or that, you typically mean that you want to leave with at least one of those. This gate remains true to its name. The only time this gate ever returns a false output is when you have a false value for both. Let's go back to our bread scenario. Let's say that we may want to buy bread if we are out of it, or if the bread we have at our house is already stale. A good way to represent this in code is, if bread equals stale, or none left, then buy more bread. Of course, coding would not be this straightforward, so instead we represent it with this symbol. Therefore, our above code would still read as, if bread equals stale, or bread equals none left, then buy more bread. Notice that we only buy bread if either of those are true. If we still have remaining bread at the house, then there is no more reason to buy bread. The next gate is the NAND gate. While there is no true equivalent to this in English, think of it as combining the words not and. This gate basically runs an AND gate that we mentioned earlier and then flips the results afterwards. Basically, you can have one or the other, or neither, but not both. Assume that a store is giving away a free sample. You can have a red cookie or a blue cookie, or you could opt to eat neither, but you cannot have both. This would be a representation of a NAND gate. Although it may not be as clean as our previous code, we could write NAND like this. If sample equals blue, and sample equals red, then no sample for you. Else, take a sample, or don't. Essentially, we said that if you have both, then you do not get a sample. We proceed to say else. which means that if the above did not apply to the situation, such as if you only took one cookie or neither, then we apply this logic. So, we fully said that you get no sample if you take both. Otherwise, you get your sample, or lack of one, and go on about your day. The next gate is the NOR gate, which is quite obviously the word NOR in the English language. However, it also stands for not or. This one will give the opposite values of any OR gates. This is the same as saying the word neither. You would want neither this nor that. If you have either, then you will output a false value. For example, say you are looking for a house that is neither in a big city and is neither super expensive. Just like the NAND gate, the code may not be super clean, but we can still represent it like this. If house is equal to big city, or price of house is bigger than what we can pay, then we will not buy the house. Else, let's buy this house. Notice that if our house is either in a big city or is more than the price that we can pay, we will not buy the house, because it does not reach the criteria that we have previously set. Otherwise, if it is neither of these values, we will then buy the house. To understand the next few gates, it will probably be easier to learn a simple gate known as the NOT gate. The NOT gate returns the opposite value of the one put in. For example, if you were to say something was true, the NOT gate would return something that is false. A NOT gate is typically represented by using an exclamation mark by an equal sign anytime you are trying to assess something in code. Some of our previous gates, such as the NOR and NAND, can be rewritten with the NOR gate to make it a bit simpler to read. The NOR gate, for example, can be rewritten as if house is not equal to big city, or price of house is less than what we can pay, then buy the house. We said in the code that if the house is not put in a big city and the price of the house is lower than what we can pay, then we will buy the house. The NOT gate is extremely useful for simplifying more complicated gates, as it can reverse the output. The next gate is called the Zorb gate, or you may see it written as EOR. This stands for exclusive OR gate. EOR stands for either OR gate. It is just like the OR gate, but you can only return a true value if you have one or the other, not both. This is essentially the same as saying the word either. You either want this or that. That implies that you do not want both. Let us say that we like red and we like blue, but not together because we don't think they match. Today we want to wear either a red shirt or a blue shirt, but not both because that would be tacky. This could be represented as this. If shirt is equal to red or blue, and shirt is not equal to red and blue, then wear the shirt. We are saying that if the shirt is red or blue and the shirt is not both, then we will wear it. Pretty simple, right? The last full-fledged basic gate is the Zorb gate, also known as the ENOR gate. It stands for exclusive not OR gate, and it typically is the hardest one to comprehend as it combines both a Zorb gate and a NOR gate. This gate is also sometimes referred to as the biconditional gate. This can simply be put as the opposite of what a Zorb gate will produce. You can think of this as the all or nothing gate, as it will never settle for anything in between. Say you want a car with tires and a brake system, like most people would. You'll only buy a car if it has both, or you're willing to opt for a pogo stick, which has neither. However, you do not want to have anything in between. You would write that using an XNOR gate. If transportation device does not equal wheel or brakes, or transportation device equals wheels and brakes, then buy that vehicle. Our code basically says that if our transportation device has neither wheels nor brakes, or if it has both, then we will buy it. Do not worry if you do not get it at first. This is probably the most complicated to understand, because it does not often arise in many day-to-day situations. Our last gate is the buffer gate. I only say it that way because it's not really a gate. It's more of a passive onlooker than anything. It sends back the same value that you put in, essentially making it the opposite of a NOT gate. If you input a true value, it returns a true value. If you input a false, it returns a false. This is only really useful on the engineering side of the gate system. Many people who use this gate in circuits return the same value but do it at a weaker or higher power in the circuit. Essentially, all you have to remember about this gate is that it returns the same thing that is put in, essentially doing nothing at all. While this video helps sum up the intro to the logic gates and helps familiarize you with the different types, it doesn't exactly cover everything. It does not describe what happens if you have more than two inputs for these functions. It does not tell you what they can be used for. It does not tell you how they can be written in different ways. And, believe it or not, it has not even told you all of the base operations yet. That is why this video is going to be in multiple parts, but I'm not sure how many yet. By the end of this mini-series, you should be able to read binary, and use gates in order to write bits and create simple logic codes. This is all for the next videos. See you guys next time, and make sure to subscribe and like this video if you want to see more of it.